Hey guys, this is Einar. I hope you're doing great today, and welcome to this tutorial where we're going to be talking about how we can conduct an hypothesis test using the t-distribution. And more specifically, what we're going to be testing is the difference between a sample mean and a population mean. And before I even move on, I need to clarify this. For this population mean here, we're actually talking about a true value. So this is not something we're going to have to estimate. We're not going to have to take any uncertainty into account or the variation around this mean into account, because this is the true value of a population. This, however, is a sample mean. So when we have a sample mean, we haven't asked everyone in the population, and that means that there is a certain degree of uncertainty that we have to take into account. Now this uncertainty is described using the standard error. Now the standard error is the standard deviation divided by the square root of n, which means that we're basically taking the variation around our mean into account, and we're taking our sample size into account as our uncertainty. And we're going to use that to standardize this difference and calculate a t-score. You might notice also that this formula is pretty much the same one we used for the normal distribution, and the reason for that is that the only difference is we're using a t-distribution instead of a normal distribution. And if we take a look at that, the t-distribution has a lot of the same characteristics as the normal distribution has. It's symmetrical, it's based on z-score here, but we call them t-scores right now. The difference being that if you consider this normal distribution went up like this, it's kind of like if we pushed down the normal distribution and made the tails bigger. So we're going to have broader confidence intervals, for example. We're going to have more uncertainty, and so this distribution is adapted for small sample sizes and situations where we have a lot of uncertainty. In fact, the t-distribution changes its appearance. So the larger our sample size becomes, the more this t-distribution goes towards normality, so to speak. So its usefulness is mainly for small samples. And if we take a look at our sample here, we can see that we have a pretty small sample. We don't know exactly how many yet, but it's pretty small. This is the population with all the villagers, so to speak, in a village, and they lived close to a nuclear power plant, the Fukushima nuclear power plant. So you can guess what's coming up. This is their attitude towards nuclear power. 100 is they love nuclear power, 0 is they really hate it. And what happens is that after we conducted this study, the power plant exploded and the whole village was burnt to the ground. Everybody was scattered all over the place. But somehow we managed to get a random sample, miraculously, because we're such awesome statisticians. Okay, so we asked them what their attitude towards nuclear power was after the explosion, and we're guessing, well, I suppose the attitude should have changed after their whole village was burnt to the ground. But we need to test this, and we need to take the fact that we haven't asked all of these people. We have only asked a sample of them into account, and that is going to concern uncertainty. So what we're going to need, if we look at our formula, we're going to need our n. So I'm going to calculate my sample n, which means I'm going to count the size of my sample, the number of observations I have. And we get that we have 20 observations, and that is under the commonly used benchmark of 30 observations, so we should actually be using the t-distribution. It's a correct situation. Our estimate of their attitude towards nuclear power, oops, there we go. Is going to be 65. Okay, so already now we can see that there seems to be a difference, right? Before the explosion, their attitude was pretty positive, 75, but after the explosion it went down to 65. Can we be sure of this guess? No, we can't, because we haven't asked everyone. We just have an indication that the attitude has gone towards the more negative, but we're not sure. We need to take the standard deviation into account in our sample size and combine them in the standard error. So if we calculate the standard deviation, sorry about that. The standard deviation. Select my data. I get a standard deviation of 19. Now, if we're going to calculate our standard error, I'm going to take the standard deviation divided by the square root of n. So I do that. The standard deviation divided by the square root of n, which is 4. So we now have basically all the parts of our test variable formula. But there's one more thing we have to calculate, and that's because, as I said before, the t-distribution changes its appearance depending on our sample size, and it changes its appearance according to the degrees of freedom. So we're going to have to calculate the degrees of freedom that we have in order to know what critical t-values to use. So I take my sample size minus 1 in order to get my degrees of freedom. And I've already found these critical values. I found them in a table for the t-scores. If you look them up yourself, you have to bear this in mind that we're working with 19 degrees of freedom, okay? So if you're looking in tables, bear this in mind. And we're going to be testing at the 99% confidence level and the 95% confidence level. So we're ready to calculate our test variable. I'm going to write equal to, we're going to take the difference between the sample mean and the population mean, because we want to know if this is large enough to be significant, divided by the standard error, which we calculated here. So I'm going to choose that there, and I get a test variable with a value of minus 2.49. And this is all we need to conduct our hypothesis test, thanks to all the tables we have of the t-distribution, etc. that we can just look up. At the 99% confidence level, we get a critical, and this is a two-sided test, so it's going to be positive and negative. We get a critical value of 2.86. So if you looked at our diagram here, it would be somewhere around here at 99% confidence level, 2.86. And what we want to know is our critical test variable in the tail, or is it located within the confidence interval that we have? And the question you need to ask yourself then is our test variable larger than our critical t-value? If it is larger than our critical t-value, it is located in the tail, and we can say that we have a statistically significant change. So let's check this out in absolute terms. 2.49 is not larger than 2.86 in absolute terms. So the null hypothesis is true. And that might seem like bad news, but it's a very high confidence level. What this means in practice is that if we conducted our sample 100 times, we would get a critical test score based on each sample that was in between minus 2.86 and plus 2.86 in 99 out of 100 times. If we would lower our confidence level to 95%, we get a different critical t-value, and we can try that instead. 95% is a lower confidence level, but it's still acceptable in most social science studies. And what it means is that if we conducted the sample 100 times, we would get a critical test score based on those samples between minus 2.09 and plus 2.09. So we ask ourselves, is our test variable larger than 2.09? 2.49 is larger than 2.09. Yes, it is. So we can actually refute our null hypothesis and say that there has been a statistically significant change in the attitude towards nuclear power in this village based on a 95% confidence level. Now, the chance that this is just due to random chance that we had this really weird sample, we just randomly happened to select a lot of people who were negative towards nuclear power, the chance of that happening is 5 out of 100. So we're saying that chance is low enough so for us to say that we're pretty sure about our guess. Basically, that's how you conduct a t-hypothesis test. I hope that you fool around with these numbers, try changing them. Try changing them so we cannot refute the null hypothesis at 95% confidence level, and try changing them so we can refute the null hypothesis at 99% confidence level, and try to understand how these parameters are all related to each other. Otherwise, I hope you have a really great day, and I hope to see you in the next tutorial. I'll see you later, guys. Bye bye.